introduction.
Sure.
Oh, sorry. So the topic I want to talk about today is event-based neuromorphic computing. Neuromorphic computing is a type of neural networks that are inspired by biological neural networks. So a little kind of different perspective from deep learning hardware acceleration. So I'm going to give an introduction to neuromorphic and position itself within AI domain. So overall, neuromorphic is a subfield of AI, which basically does processing based on neural networks, based on the what is observed in biology. So first, I'll start with the Continental Corporation. Continental Automotive is a group of is a subgroup of the Continental Corporation. We have 500 locations over the world in 61 countries, 230K employees, and so AI has been transforming the continental traditional businesses, even tires, like for inspection or making smart tires, but as well as advanced driving assistance systems like ADAS. We have a large market share in automotive electronics, about 30% worldwide. And we have been active also in automated driving from perception, planning, and control. So for perception, we have smart sensors, like radars and cameras that come with perception modules. We are running intelligent intersections in California, Michigan, and outside US as well in China. We have V2V, V2I connectivity infrastructures in this kind of intelligent intersections, and we are making also autonomous driving platforms. Here is an example of it, a Cube, which has been deployed in Frankfurt and Michigan. A driverless, basically, car to collect data. So back to computing, we know that VLSI scaling has been driving the performance improvement for microprocessors. The graph shows the different metrics for single-thread microprocessors. The one in the blue is showing the performance, basically, which we see in the graph about 2005. Basically, the performance improvement for single-core microprocessor has flattened, and the main reason for that was the difficulty in scaling frequency. So we know that a number of transistors, the above curve basically is, so the one in red is basically showing number of transistors, while the number of transistors doubled every 18 months and continued the trend, but the microprocessor performance has not grown as much from 2005, related to issues like clock skew and scaling frequency. But about the same time, there has been a trend on increasing number of the cores to increase the basically performance of the system. About the same time, there has been new trend for computing requests. We see example that kind of computing request that has been processed in 2017 per minute. So this is a lot of computation, and it requires new computational models to basically deal and process this kind of requests. So new compute platforms need to process unstructured data, text, video, and it needs to interact with the environment and be adaptable. For example, autonomous driving is one of the examples that you need to perceive the environment and act accordingly and be adaptive to the basically changes and make a right decision basically in the moment. So this also requires large amount of linear algebra, tensor processing, and in hardware that means more parallel structure and more performance basically. From memory side, we have an increase in the amount of memory that we need, and the higher bandwidth and lower latency memories, especially for locality, and use the data local so that you can reduce basically bandwidth requirement. So it will be critical basically to do near memory computation. So AI is basically touching every level of hierarchy, from application to device and process, kind of the materials that has been used even to build the systems. Now at the application level, we have video and images basically face recognition, object detection, overall autonomous driving is one of the major applications of AI. Audio, we have a speech recognition, NLP algorithms. We have traditional machine learning algorithms like SVM, KNN, or more bio-inspired learning algorithm like spike, timing-dependent plasticity, different topologies we have. But because of the performance of AI algorithm has been so good, there has been changes also in software toolchain, development of new softwares like TensorFlow, but also had impact on chip microarchitectures, many core SoCs or programmable chips like GPU, even a trend for brain-inspired computing neuromorphic chips. So on the device level, that also imposes some constraint. You need higher bandwidth memory, HBM, or higher interfaces like optical interfaces, or NVIDIA, basically NVLink, the new NVIDIA interface for GPU and memory combination. On the emergence side, we have ReRAM, we have phase change RAMs, or analog memories like memory store, which basically has use in kind of distributed memory structures. So, So in terms of workflow, we know we have the training and verification in developing deep neural networks. We have inference as well in the bottom, but there is also in middle, there is a step basically to translate what you have trained on the deployment side. So for training, we have large data sets like ImageNet. There is a pre-processing algorithm development. And in application like autonomous driving, which is safety critical, we have an important step like it has to be verified, form of formal verification maybe. And then once this model are trained and verified, we can basically use existing hardware architectures, which basically right now they are not so performant to basically fit all this model in it. So there is a need for new development of hardware that requires basically optimization, like graph optimization or quantization. And you need a throughput requirement from your application basically to develop a hardware architecture for this. So in terms of microarchitecture, we can have von Neumann-based AI chips, which basically there is a distinct physical distinction between the memory and compute. So at some point, this will lead to memory bottleneck, even in more sophisticated hardware accelerators, that there are local memories, RAM, SPRAMs, and so on, local to computation. But if your model does not fit there, at the end of the day, you end up with memory bottleneck. So alternative to this is a computing technology that co-localize memory and computation. In memory compute architectures and neuromorphic architectures are example of that. That basically you have the memory next to computing elements, so you don't have a main memory to go to. So this is inspired also for neuromorphic architecture, at least by biological neural networks. So neuromorphic computing, basically, which is inspired by biology, from biological point of view, the motivation is to understand brain through engineering. You develop a larger scale model, hardware systems, basically, to model what has been observed in neuroscience and try to understand the process of computing. And from engineering point of view, there are a lot of lessons that can be applied for real-time vision or speech and pattern recognition. And it covers biology, theory, and engineering. So from biological point of view, there is neuroscience study to extract basically computational models for memory and computing, vision, and other sensory systems. From a theoretical point of view, you can develop models basically based on what has been observed in biology, and at the architecture level in engineering side, that also applies some constraint to the hardware architectures and kind of devices that you use. For example, memory store as a device is an analog memory which is a good fit basically to implement neuromorphic models, because it provides a multi-level analog memory next to compute with a very compact and area-efficient way. So neuromorphic basically bridges between these three fields. And so the motivation for this is a brain basically with 86 billion neurons and 500 trillion parameters consumes 25 to 40 watts of power in comparison to other AI models, basically much smaller and require much greater basically powers. So there has been neuromorphic chips developed over years. IBM TrueNorth is one of the examples that consumes only 65 milliwatts for typical networks, or DNAPS is running 5-layer spiking CNN, a neuromorphic version of CNN for few classes of the objects, which only consumes a fraction of what we have in the microcontrollers even. So that makes it perfect fit for IoT or autonomous sensory motor systems and brain-machine interfaces. Sorry. So at the big picture, the neuromorphic models versus AI hardware accelerators or deep learning hardware accelerators, from computational point of view, in inference, for example, AI models are more compute intensive but less biological accurate, while Spinnaker or TrueNorth, DNAPS, those are examples of neuromorphic chips, basically, which are more biological accurate. There are spiking models, silicon retina, locomotion. Those are another examples of more biological accurate and less compute intensive models. From training point of view, the deep learning is more sophisticated, obviously, and there are better tools to implement this kind of models. While for neuromorphic models, STDP or can go back. STDP memory store or ReRAM-based synapses are example of more biological accurate type of learning, but there are no tools developed for this. Also, there are they're in research phase basically to develop kind of software frameworks to implement STDP learning rules, for example. In terms of algorithms, neuromorphic algorithms, they can be represented as a graph which contains neurons, synapses, their parameters, and their connectivity is through edges in the graph. Execution model is where it distinguishes itself from deep learning. I mean, massively parallel is the same, but asynchronous computation is what makes neuromorphic models more energy efficient. So you process data as there is a data, otherwise there is no processing of the data. But the recent development in areas of speech or vision and deep learning has been also a momentum for neuromorphic models, basically for more research on this type of computation. So basic computing in neuromorphic models is basically the information is through digital binary pulses that is carried around axon at the top, and it's weighted through this transistor, for example, and it gets accumulated on some capacitors. The neuron is looking at this voltage, and upon reaching a threshold, it generates a spike. Basically, it's giving new information to the destination. So traditionally, these models, they have been implemented in mixed signal. Back in the day, in analog subthreshold was a most compact form to implement this type of circuits. And asynchronous computation obviously more efficient because it matches with the nature of computing. So neural networks in neuromorphic computing, they have 1,000 to 10,000 fanodes, unlike digital circuits that we have few fanodes. So that makes it challenging basically to make big models of neuromorphic. But but the recent advances in CMOS processes, it's make it possible to basically a group of neurons make a module, and using network on chip and on-chip routing to make a big network of these models. So like IBM TrueNorth has 1 million neuron on a chip, and 16 of these chips make 16 million with basically milliwatts of power consumption. But another area that neuromorphic has been more, I would say, progressive than computing part as neuromorphic sensor, because in biology it's easier to study the sensory systems like retina and cochlea. So that has been more progress on that side. And so event-based camera is basically a neuromorphic device versus a standard camera. So in a standard camera, we have a fixed time frame to output the result of the pixels. And that's for a regular camera is like 30 milliseconds, or if it's faster, it's like 10 milliseconds. But a neuromorphic sensor for vision is asynchronous, and it produces output at microsecond resolution. So if there is changes in the scene during that delta time frame, it outputs basically what it sees. And if there is no data, it will stay silent. And the data, an event in this type of sensor is the timestamp, the coordinate of the pixel, and the amount sign of the changes, that if the light intensity for that pixel decreased or increased. So a simple graph to show that at the top is a standard camera for a rotating dot in the scene. So a standard camera, every delta time, basically produces an output which shows the location of the dot. But in DVS or neuromorphic sensor, you just see basically the changes in the scene. So just shows the pixels that are representing the dot, the rotating dot in the scene. So that makes it a lot less data basically to compute, and it's only showing the changes in the scene. So, and you can get understanding of temporal differences between the frames, and on the paper it should reduce a lot of computing. So versus high speed cameras like Fastcam SA5, which produces also 1 mega frame per second, the resolution is, so for resolution for event-based at 2 mega frame per second is much higher than this kind of fast cameras, because they group basically pixels, and to reduce the amount of to increase the number of frames that they can produce, they have to reduce the resolution. So it will be much lower resolution. They have 12 bit per pixel in event-based. This example from Samsung product is just 1 bit. The data rate is order of magnitude difference. And power consumption for this kind of high-speed camera is so high that you need active cooling, unlike the event-based cameras. Dynamic range is another feature of this type of cameras. That is 100 dB is quite high for most application, to go from very low light condition to very bright conditions. So it works in dark situation as well as to very bright light condition. So one of the experiments we did with this is to use that kind of camera for pedestrian detection. In autonomous driving, pedestrian detection is one of the most critical one, and it's usually even redundant approaches are useful, because safety is one of the critical things in autonomous driving. So we tried to use this camera with the neuromorphic model that you need to develop, as well as we tried it with a deep learning example here, YOLO, to see how, if we can process those kind of data and how we can basically do optimization. So the idea for that was that we get a lot less data, so you have more opportunity to optimize the activation and reduce amount of data for memory as well as for computing. So in regard to spiking neural network, that's a little harder to develop because you need large data sets, and there is no available, publicly at least available large data sets. So that's one of the challenges, but we have been collaborating with the team from Samsung, which they have 1 million labeled data, so that has been very beneficial to our work. So the example I showed here, so from event-based camera, basically we get pixel data, and to use it with a deep learning model, because they are frame-based, we had to make frames. So in this example, the YOLO example that I use, it's a 20 frame per second on our hardware. So we accumulate the event data for 40 milliseconds to make a frame, and basically feed it to the deep learning model and see the output. And here is just showing an output of YOLO for detecting people, this example we have. So another feature of this, you have a lot less data to process. So, and we have been, our goal is basically is not to use this camera with the deep learning models, but even if for some application, if that works, there is a lot of opportunity for reducing amount of data, compressing data, less computation, and max set. But our goal is to have neuromorphic models that are trained on this kind of data. And again, the difficulty with that is the large data sets. So the potential of neuromorphic is a little far from, to be a product. From sensor side, we have already like neuromorphic sensor used in smart home systems by Samsung. But from computing side, there is still in research, and the problem that they are facing right now is a lack of new training algorithms, and that's because of the data sets, large data sets are not available. But the advantage it offers is power efficiency and minimum amount of processing that you need. So unlike the deep learning models that basically you train your models with a lot of data, and then you make effort to optimize graph for quantization, sparsity, use sparsity basically for compression, reducing amount of memory. Neuromorphic models, you do that right in the beginning basically. You basically collect only useful data, and you want to train your models with minimum amount of data that you need. So high dynamic range, working very low light condition, very bright situation is another features of vision sensor that are basically provided by neuromorphic sensors. And with that, I think I've finished my presentation.
Great. Any questions? Yes.
So in the last video that you showed, is the sensitivity to just changes in pixels, or is there some pre-processing of what you're interested in trying to detect?
So pre-processing for this example, the only thing, it was denoising. So from the pixel, we have from the camera, we have a lot of bad pixels or noisy pixels. So okay. The only pre-processing was to remove those kind of data.
Yeah, okay.
And that was not sophisticated noise reduction algorithms. It's just there are some bad pixels because of the yield that we need to remove.
Yeah, we can take one more question, then we'll move on.
Have you been looking at stochastic computing as an alternative framework?
That's a good question. So one of the areas in neuromorphic computing is basically to take deep learning models, convert it to a spike-based version of it. So, but that's, I'm not sure that will be very useful in all scenarios, because the amount of data that you need to basically represent with a stochastic representation sometimes is over the raw data even.
Okay, thank you.
No problem.
Thank you, Saber. Great presentations.
Thank you.
Okay.